Let's complete it now. Evaporative simple air cooling system. We need to calculate the mass of air bled of the main compressor. This one, m dot. Okay. So equation, m dot is equal to refrigeration effect is given. So m dot Cp T6 minus T5 dash. So let's start finding all the temperatures. T5 dash will come from T4 dash, T4 dash will come from T4, T4 will come from T3 dash, and start doing the same thing. So you know already, but here the new thing which we have here for this heat exchanger, effectiveness is given. 1, 2, 3, 4. 4 dash, 5 dash. And this is 0.3, actually actual point is 3 dash. So how to calculate for 3 dash? Efficiency of compressor is given. This one, isentropic efficiency. So find out T then T3 dash from here. So you know already. Then we need to find out T4. Effectiveness. So effectiveness is equal to actual heat transfer will be T3 dash minus T4 divided by maximum possible. T3 dash minus T2. Okay. So from here we can find out T4 because this effectiveness is given as 0.6. Okay.
It's not even if it does one.
Yeah. If it's not given. Then T4 dash, what is given? So T4 dash is equal to T4 minus 5. That is given. So that's how we can calculate T4 dash now, T5 dash from efficiency of turbine. Okay. Okay, so then power required m dot Cp T3 dash minus T2, power required of compressor COP, okay, refrigeration effect divided by power of compressor. So here is the complete solution. There is nothing complicated. The mathematical steps which you have to do. Should I repeat something here? I think it's just now simple mathematics. So you can solve this problem, okay, easily. Mass flow rate of air. Now you can find out from here. This refrigeration effect is given in tons multiplied by 210 if we want answer in kilograms per minute. Power required of compressor, okay. Kilowatts, now you should know why there is 60, why there is 210, okay, COP 0.094. You have to convert tons to something. Now it's up to you whether you want to convert it in kilowatts. If you will convert it in kilowatts, mass flow rate will come in kilograms per second. Okay, so that is also fine. He is doing it in kilograms per minute. So it's up to you. Okay. Now, next configuration of an air cycle refrigeration system is called bootstrap type cooling system. Bootstrap, right? If you're boot, what you do? That is bootstrap. It is very similar to that one. So they name it as bootstrap. Now, what is happening here? It's clear. Look, 1 to 2, ramming, 2 to 3, compressor, but what is the difference? 3 to 4, cooling, then 4 to 5, another compressor. 4 to 5, another compressor, then 5 to 6, same cooling from the same ram here. Okay. Then 6 to 7, turbine, 7 to 8. Now, what is the advantage of doing this? Look, if this compressor was not here, then this would have been where it would go on to turbine. If 3 to 4, after 3 to 4, there will be a turbine directly in the previous system. But here, no, less refrigeration effect. Here we can produce low temperature. Here for maybe we end up here. Now we again compress, again cool. So we are going further away from this region, in other words, so that we end up to a very low temperature. Right? That is the logic behind it.
Further away in terms of what? We go from 3 to 6 further away.
Yeah.
In terms of what?
Temperature.
But T4 is
In pressure.
T6.
Hmm?
T4 is this temperature.
Yes, but look where we will end up here. This temperature is higher than this one. This is the last point now, which the temperature at which the fluid is entering into the cabin. Right.
COP may be less.
COP may be less, but where we use this system, I told you when the aircraft speed is increasing, means this velocity is increasing, means this temperature will be increasing. This 0.2 temperature will be very high. So at very high velocity, we go for such systems because your T2 will be very high. Okay. So here nothing new, just that new compressor, and you do not need to supply any energy to that compressor. That turbine output is used to derive that compressor. That's why maybe COP is not, we cannot say with surety, because here we have a turbine output which is used to derive that compressor.
So this is the same application as the one with the evaporative cooling, except no evaporative.
Yes, no evaporative cooling. Evaporative cooling is simple, just fluid. Here you have another heat exchanger, another compressor. So for that, to decide which one is better, you have to do some more detailed calculations, more economic analysis, which one is better. Okay, but this is another type. Yeah, let's discuss it. So this is called bootstrap type. So calculations are again not that difficult. Of course, you have to make some more energy mass balances. How much mass is going there? How much mass is going there? So the design of that heat exchanger, because we are not designing heat exchanger here. We are just solving this heat exchanger with the help of effectiveness. But actually, you have to design that heat exchanger, the procedure which you learned in heat transfer. Okay, so that part you already did.
The mass is always the mass of 3 rods.
Mass of 3. Yes. So far, yes. It is the same mass which is flowing. Yes. So far, yes. But there is another system coming where this m.3 will be split. Okay. So this is called bootstrap type cooling system. Okay. Any question from the schematic or TS? Hopefully it's clear. Ambient pressure, This is cabin pressure, ramp pressure, first compressor, cooling, second compressor, again cooling, isobaric, everything is now clear hopefully. Isentropic, look that term isentropic. The use of that term isentropic. When we were learning entropy, we hate that concept, but that isentropic concept which was there, it is so useful to design these systems. Even if you do not know entropy, but at least you know isentropic, use it. Yes. Design it. Okay. Ideal gas, non-ideal gas, whatever we learned in thermo. So it's just the application of this. Okay. Okay, so all those processes, they are explained here. And you can read it by yourself. There is nothing difficult here. Okay. Now in this case, the mass flow rate of air we can find out from this process. Okay. What else? Power required for the compressor. Only you are providing power here to run that compressor. For that compressor, we are getting this work output from the turbine to run that compressor. Okay. COP is again this divided by this.
This is the percent of the wall.
Power of compressor. Here the P means power. Refrigeration effect divided by power. Again, these numbers you should know. That is up to you in what units you are working with. Here he is assuming Q always in tons. That's why he's multiplying with these numbers to convert it in kilograms per hour or kilograms per minute or kilogram per second, because he's assuming Q in tons. If you say Q is in kilowatts, then there is no need to write these numbers. Okay.
And you can put 3.5 instead of this.
Yeah, 3.5, or just simply say Q over P. When you will solve problem, then I will see what number. Okay, so do not get confused with this thing. Okay.
And the power is both added together, right?
Now
Only the main compressor.
only the main compressor. See the schematic again. Second compressor is run by turbine. So no need to provide any extra power from external source. So that is called bootstrap type cooling system. Another version. Here we have regenerative cooling system. Now you can easily identify by yourself what is the difference here. Yeah, we are regenerating. Yes. This cooled air is reused here in the second heat exchanger. Okay. Walaikum assalam. There is no second compressor, but here the amount of mass, some is taken back to cool in this second heat exchanger. So 1 to 2, ramming, first compression, 3 to 4, first heat exchanger, 4 to 5, another heat exchanger, 4 to 5, then 5 to 6, turbine, 6 to 7, refrigeration effect, but here mass flow rates are important. Now again, what will be the mass flow rate here, which you were saying, it is now it is different. Okay, because here this mass is splitted into two parts. So for Q dot C, it should be M dot A, which is different from this one, M dot 5. Right? So M dot A will be equal to M dot 2 minus M dot 5, or M dot 2 minus M dot 1. This M dot, which was flowing here.
But texture is split also, right?
Here it's also splitted. So okay, let me say this is M1. The mass which is going into the jet engine, we are not considering that one.
From 1 to 2 is without.
It's the same. Yeah, it is actually the total mass entering. So let's Yeah, so it's better to say m dot 3. Or I am saying this is here, I'm only considering that mass which will flow here. And neglect that one which is going into the jet.
So the number will be next to or
M dot A, yes, it should be written as M dot 1 minus M dot 2. Right. Or M dot 3 minus M dot 2. Right. So here in this heat exchanger, we have two different M dots. One is M dot 2, other is M dot 1 in this heat exchanger. Okay, processes are clear. Yes.
And 0.8,
0.8. Where is 0.8?
0.8. Where actually go the original light of cooling air outputs? Atmosphere.
Here, atmosphere. Yeah. If you want to use, okay, use it for some purpose. But here, so we do not need it. Okay. Okay. Here we can write another equation for this heat exchanger. Heat lost by this fluid is equal to heat gained by this fluid. So m dot 2 or yes, m dot 2 here is naming it as m dot 2 into Cp into T7, no, T6. This is T6 minus T8. This is the heat lost by that cold, heat gained by that cold fluid is equal to heat lost by this hot fluid, m dot 1 Cp T4 minus T5. Because we would need that equation when you will solve a problem of this regenerative heat exchanger. So here we can write an equation of maybe m dot 2, this one, right? If temperatures are given, then I can find out m dot 2 from here. What about T8, temperature of air leaving into the atmosphere? Okay, so all these equations, when you will be solving problem, then you will see which one equation to use to find which term. Okay. So he is just mentioning all those possible equations. All right.
This equation will be given in Excel or
This equation, what I should give? Maybe you say 1, 2, 3, and you may say this 3 dash, then it will mix up. This is simple equation. Heat lost by one fluid is equal to heat gained by the another fluid. Whatever notations you have chosen, use it. Otherwise, I will give it here and you will say my 6 and your 8 is not same. So then we will have issues. So this MCP delta T is an equation if you ask me to give in the exam. Shift back to semester 1, MCP delta T. Should I give this MCP delta T? Okay, that equation maybe I will give. This T2 by T1 is equal to P2 by P1 to the power, that's one. Okay. This one will be given, but do not ask MCP delta T or M into HFG or M into delta H. These equations doesn't make any sense to give. Okay. And that is what we are using because we are solving only the thermodynamic part. Yes, if we start solving the heat transfer part, then you need those convection coefficients, Nusselt numbers, then of course. So, but we are not solving the heat transfer part, only the thermodynamic part. Okay. Okay, so here is the regenerative, that is the power output of the power input to the compressor. Okay, COP. Example we'll solve because that is the a bit complicated example for regenerative heat exchanger. Not complicated, but some extra steps in it. So we'll do it in the next class.